I have to do an example on Jacobian, but since we have enough time, I'm going to talk about a new topic, and one of the things that we'll pull together is some miscellaneous topics that are left, and we'll cover them all in one class. So for today, let's talk about path planning. Okay. We spoke about positioning and we spoke about tracking the manipulator's velocity. So we did kinematics, right, which is your positioning. And we also spoke about the Jacobian, which tracks the velocity. Okay. So now what we can do is we can look at how we can move from point A to point B in the workspace. So let's say you have point A here that you want to be at, or you're starting from X, Y, Z, and you want to go to some point B, which is Q, X dash, Y dash, and Z dash, right? You want to move from here, you want the manipulator to move from here to here. There are two ways to do this. The first way is planning the path. That means it should know what path to take from A to B. You can do this in Cartesian coordinates. Or you can do this in joint coordinates. Or let me call it as joint space. Okay, Cartesian space or joint space. What is Cartesian space? Cartesian space is your three-dimensional space, which is this. You can also, if you want to add, you can add your orientation also here, phi, theta, and psi. Same thing here, because if you're changing the orientation, you can also include that here, phi, theta, and psi. All right, now, when I do Cartesian space, what I'm doing is I'm defining a trajectory from P to Q in terms of X, Y, and Z. When I talk about joint space, what I'll do is I'll see that in moving from A to B, how do my joints move? So there will be a trajectory. Let's say this is A. For example, this is a 3 degree of freedom. Obviously, if it's a 3DOF, you won't have the angles. But let's assume for now that it's a 3 degree of freedom. So at A, I'll decide my joint position, my joint displacements. And at B, what does it lead to go to B? So I can define the trajectory of going from A to B in X, Y, Z, which is in Cartesian coordinates, or I can define it in joint space like this. Now, if I had a choice, which one is more practical to do, joint space or Cartesian coordinate space? Which one would we prefer if we had an option of doing? Should we plan a trajectory in Cartesian space or should we plan a trajectory in joint space?
I think joint space.
Why?
It seems easier.
It seems easier? Okay. The problem, okay, it's joint space is preferred and I'll tell you why. But the problem with is that it's not as easy as you think. The only reason being here, you have to compute the inverse kinematics, right? So at A, you'll compute the inverse kinematics and find the set of joint angles that you need to be at A. Same thing, you'll compute the set of inverse kinematics to find the joint space or the joint displacements to be at B. Now, in some cases, for example, a 2 degree of freedom manipulator, you can have a choice. You can have more than one solution. Okay? So if you have greater than one solution, then you have to pick a solution that you want to go with. Okay? So sometimes you'll end up with a choice of solutions that you want to take at all of these points. The reason it is good is because, let's say I'm going from A to B, right? And I plan this trajectory like this. Okay, the manipulator trajectory like this in Cartesian space, which is X, Y, Z. All right, let's forget about the orientation. So each of these via points, I'll plan the manipulator should be at these points at a certain instant of time, because we are not only tracking the position, you're also tracking the velocity of the manipulator. So it should maintain a certain velocity. It will start from rest. It will track these points and it will go to B. All right. Now what will happen is, if I plan this, let's pick this point. Let's say this is some point x3, y3, and z2. Okay. Even though I've planned my trajectory, when I try to go to this point by computing inverse kinematics, I might realize that there is no solution there. Okay? If you plan a trajectory in coordinate space, you might end up with a point within the trajectory, if you have not checked, that might have no solution. Or sometimes it could have a singularity, right? Which is your determinant of your Jacobian is 0. That makes motion very difficult at those points, right? So it's better to plan a trajectory in Cartesian space so you can avoid going into points that have no solution or when the determinant of the Jacobian is non-zero. So to do this, what we do is we try to plan, in most cases, we plan the trajectory in joint space. Okay. The whole set of joint space is represented by capital Q. Q, that means any joint that you have belongs to the set of numbers, which is the joint space. Now when we talk about joint space, what we do is we try to come up with a set of equations that can define a given trajectory. There are different methods. We'll start off with what is called a cubic trajectory. Now, using it, there are two things that we are trying to track. We are trying to track the position of the end effector and the velocity. Okay. So our method should give us two things at least, at a bare minimum. Ability to track the position of the manipulator at any given time on the velocity. Okay. So in this case, to do so, what we'll do is we'll set up a set of initial and final conditions. Okay. So at initial condition, at this point, initially t is equals to 0. So I'm starting time when t is equals to 0. And we'll stop at t equal to tf, which is your final time, which can be nth. All right? So what I'll do here is, we'll say that it starts, let's say that it starts at a position, initial position is q of 0, which is my initial position. Okay? So this will be my initial position. Initial position is q naught. Q of 0 is my initial position, q naught. Initial velocity q of 0, we'll call it as v naught.
Professor, again, when we move from point to point, why velocity is important?
Velocity is important because if you're only tracking the position, it does not matter. You can go as slowly as you want. Okay, but we are trying to develop a system where you can not only track the position of the end effector, but you can also track the velocity. Okay? If you're just moving from A to B at your own leisure, you can always move like this. There's nothing to track, right? If there is no time scale, there's nothing that you can put it in a framework because you're not tracking anything if there's no timeline, right? If you do this independent of a timeline, you're not tracking the motion. When you start tracking the motion, you differentiate with respect to the timeline, you'll get your velocity, right? So at this point, the velocity should be this. At this point, there has to be a timeline of events so you can track it on a timeline. Okay. Same thing here. Your final position, right? Q of Tf, let's call, will be Qf. Okay. And your final velocity of TF will be equal to. So these four things should be taken into consideration. You want to start at a certain velocity, at a certain position, and you want to again stop at this point. So this is, you can call these set of conditions as your point A, and this set of conditions as your point B. So we are tracking the motion of one joint here, because we are doing this because we are all talking about Q's here. Initial velocity will be Q dot, and this will be Q dot. Okay, this is in joint space Q, because we are talking about doing this joint wise. So we do the same approach for every joint. So let's consider this one joint, and then we can extend this to all the joints. All right, when you have four variables here, four constants, 1, 2, 3, 4, the only equation that can take care of this, the minimum degree equation, will be a third order polynomial. Okay, when you have four, you need a we need a third order polynomial. So we'll say that Q of t will be equal to A naught, A1t, A2t squared, A3. Okay. So these four coefficients, you need to find these four coefficients A1, A0, A1, A2, A3, such that these four conditions are satisfied, which is at Q equal to 0, the position should be Q0, the velocity should be V0, and at final time Tf, these should be the conditions, which is Qf and Vf. So these four coefficients should be such that these four conditions are satisfied. Okay, that's why we cannot use a second degree polynomial, because then you will have only three coefficients trying to suffice the four conditions. Here you have four coefficients of the polynomial trying to satisfy the four conditions. Okay, so this type of a trajectory, because the order is 3, is called a cubic or spline trajectory. Alright, so in this case, we'll say that at t is equals to 0. Okay. At t equal to 0, Q of t equal to 0 will be equal to A naught. All of this will be 0 because time is 0. And this is equal to Q0. Right? Because at t equal to 0, the initial position is Q0. Alright. So by extension, we can write that if I differentiate this, Q of t, this will be equal to A1 right? So we can say that Q dot of t equal to 0 will be equal to A naught is obviously 0. This will be equal to V0. Okay. This is your initial condition. Let's do the same thing for the final condition at t is equals to Tf. This is your final condition. At t equal to Tf, we will have Q okay. This will be equal to A naught A1 Tf plus A2 Tf squared plus A3 TF cube, this should be equal to Q. Okay. Same way, velocity. We're trying to track the velocity. Q dot of T is equals to TF. A naught, we don't have an A naught. So this will be A1 to A2 TF plus 3A3 TF squared will be equal to VF. So from these four equations, in this case, we know the coefficients, we know the final time. So time can be, in this case, starts at t equal to 0, let's say stops at 3 seconds, 4 seconds, 5 seconds, whatever you might decide is your final time. So in this case, in this set of equations, this is known. These parameters are known because these are the set of initial conditions that you're starting with. We know these values. We know TF. TF is known. T0 is 0. So the only thing is, how do we find the four coefficients? So if you call this as equation 1, 2, 3, and 4, we can write this in a set of linear equations. We can set it up as a matrix. So we can say A naught, A1, A2, A3. This will be equal to the set of four independent variables, which is Q naught, V0, QF, and VF. So this coefficient of A naught is 1. So this will be 1, 0, 0, 0. Here A1 has only 1 in this, so 0, 1, 0, 0. Here it will be 1, TF, TF squared, you'll have TF cube, then you have 0, 1, 2 TF, and 3 TF. All right? So this time matrix is known. This matrix, let's call this as T. This is known. This is a constant, so we'll call it as T. This is your coefficient matrix A, and this is your constant K. Okay? These are known. So this matrix is known, and this one is also known. Right? So we only need to find the matrix A, coefficient matrix A. You can solve this as linear equations. We'll do an example, but this is much easier if you're programming it, doing like this makes more sense. So T A is equals to K, you need to find A. So A will be equal to T inverse K. Okay, so T inverse. It's a square matrix, so you can be able to find the inverse. So you'll be able to find all the coefficients like that. Let's try to solve one problem, then we'll go to a very special case where we can actually program this as a direct analytical solution. Okay, let's take one example here, which is okay. A joint displacement of 10 degrees, okay, starts from rest and stops at 40 degrees after 1 second. Okay, after 1 second, it stops. Define the motion of the joint using a cubic trajectory. Okay. Set up the initial and final condition, then we can solve this. So, the joint displacement of 10 degrees starts from rest. So, at t equal to 0, initial condition, at t is equals to 0, you have q0, or let's call it as q0. q0 is how much? 10 degrees. V0, because it starts from rest, this is 0. Okay, 0 degrees per second. Okay. Same thing here. In the final condition, T is equals to TF, which is 1 second. Okay. In this case, QF will be equal to 40 degrees, right? And VF is 0 degrees per second. Starting and stopping at rest, so the initial and final velocities will be 0. Okay, this is your initial displacement, that's your final displacement. So we need to find what is A0, A1, A2, and A3. So we need to define the motion, so you'll have the cubic trajectory. As follows. Q of t will be equal to Q. Actually, A0 will be Q0, A0 plus A1t, A2t squared, A3t. Right? So you'll tell me what is A1, A2, A3. So at t equal to 0, when you substitute t of Q of 0, this will be equal to Q0 plus 0, I'm sorry, A0 plus 0 plus 0 plus 0, right? This is equal to your initial position, 10 degrees. So A0 will be equal to 10 degrees. Right? A0 is 10, let's call this as 1. Let's track the initial velocity, V0. So this implies, obviously, that Q dot of t, right, which is V of t, will be equal to so here we can say A1 plus 0, because time is 0 here, plus 0 is equals to 0, because initial velocity is 0. So in this case, A1 will be all right. Let's go to the final condition. Q of 1 second, right? T is equals to, in this case, final condition, T is equals to 1 second. So this is your final time. Okay? So in this case, here you'll have A0 plus A1 plus A2 plus A3, right? Because all of these are 1, will be equal to 40, right? We know A0 is 10, so this is 10 plus A0, I'm sorry, A1 is 0, this is 10 plus all right. Now we can find V, same thing for the final velocity. V of 1 will be equal to here. This is 0. A1 is 0. So you have two equations, A2 plus 3A3 is equals to 0. Solve 3 and 4, tell me what is A2 and A3. From 3 and 4, tell me what is A2 and A3.
A3 is minus 60 and A2 is 90.
A2 is
A2 is 90, A3 is minus 60.
A2 is 90 and this is minus 60. Double check this for me. They can be 6 and 9 also.
That's 30.
Yeah, that's 30. We'll have to remove this because these are coefficients, they won't have any. Okay, double check this. So once you have this, you can write Q of t, which was A0, A1t, will be equal to Q of t will be equal to A1. A1 is 0, we only have A0, so 10, A2 plus 90, t squared, minus 60. Same thing with your velocity, v of t. Okay, v of t is here, A1 is 0, so 2A2t, 2A2t will be 180t minus 3 times this, so this will be 180. This will be degrees per second. This will be degrees. So when you plot this, when we plot the velocity and the position, so let's say we want to plot, okay, let's say this is your position Q, and this is your velocity V. You start from t equal to 0 to t equal to 1 second. Okay. Your position will go something like this. You're going from 10 to a final of 40 here, right? So if this is 10 here, and let's say this is 40, a cubic trajectory will be like this. It will start from 10 and go like that. Okay. A velocity profile will be like this. This is your Q of t. Velocity, you're starting from rest and you're stopping at rest. So the velocity will be starting from rest. It will be a Gaussian curve like that. This will be V of t. Okay. This is what V of t will be like. because you're starting from 0 velocity and you're stopping at 0. What about the acceleration?
One more derivative.
I know, but what would it look like? What would it look like if you want to look at the acceleration? So in this case, your acceleration will be A. Right? Okay, so what happens to the initial acceleration from here? A naught, A of 0 will be 180. A of 1 will be equal to, right? It's a non-zero acceleration. That means the acceleration will be something like this. At t equal to 0, my acceleration will be 180 here. Let's say this is plus 180. And this is minus 180. All right? That means it starts with a very high acceleration and it stops with a very high deceleration. Negative means it's decelerating. That's all it means. It's trying to brake. So it will stop here with a very high. The reason we have a high values for this is because this cubic polynomial, in this case, you can only track Q and V. You can only track position and velocity. There is no room to track the acceleration of the joint. So in this case, this will come up with anything to satisfy the conditions for this Q and V at initial and final points. There is no room in the equation to track the acceleration for us. So even if you have some initial and final values, obviously when you stop, you want to have a 0 acceleration. You don't want to have such a high acceleration when you stop, right? Because if you stop with such a high acceleration, it will topple over the manipulator. It's like, you know, when you're driving and you hit the brakes really fast, you try to move forward onto the dashboard. So same thing with this. When you try to brake so fast or when you try to take off so fast, you're creating a motion that will knock the manipulator off, because this manipulator is only grounded at one place. You have the manipulator that is attached to the base here, like this. When you start moving so fast and you stop so fast, it will try to create vibrations or it make the manipulator very unstable. So you try to avoid this situation, but in this case, this works when you're doing this at a very small velocity, where you don't need acceleration to be 0, or you're trying to stop, or you're moving at very small, minute velocities. This is fine. But when you want to do tracking the acceleration also, then you have to move towards a higher order polynomial. Before we get to that, let's do one thing so that we are able to program this when we do the lab exercise. Let's develop a generic model for a unit time trajectory. Okay, so we can use this to program it. So what we'll do is we'll try to develop a simple model for a unit time cubic trajectory. To calculate, obviously you can use the matrix method. It works perfectly fine if you want to do it like that. But you have to set up the matrices. You'll have to do that when we go to the next one. But in this case,